Right. So, here is where we stopped, right. We said that intensity is A star into A star, and we said that provided the result first. We said that when you lock n number of modes together, so that their phase difference is not a function of time, then you get pulsed operation. Repetition rate is not a function of number of pulses that are locked, pulse width is. That is an important take home message. See, repetition rate is 2L by C. All that is important there is what is L. L tells you what the repetition rate will be, right. But pulse width, that is where number of modes come in. So, now let us see how. So, we start our somewhat sketchy discussion of mode locking. I apologize for the quality of slides. Slides that will uploaded will hopefully be better. I tried to do things quickly, and this is another moral lesson that you do when you try to do things quickly, they do not work out to be very good. Okay. So, as we said in the previous module, we do not really have plane waves. We have damped oscillation, but then eventually the way we go from time domain to frequency domain is Fourier transformation. And the beauty of Fourier transformation is that to get the correct information about frequencies, it does not matter if you take a plane wave or a damped wave, because they get separated. So, that makes the mathematics a little easier, otherwise we would have another damping factor here. So, we are going to work with plane waves, where we will say that this electric field is a function of time and is given by E0, the amplitude, maximum amplitude, into e to the power I omega t. What is omega? Yes, angular frequency. Omega is angular frequency. What is the relationship between omega and nu? Frequency and angular frequency? 2 pi. Now, just all you have to know is whether to multiply by 2 pi or divide by 2 pi, it is not very difficult, right. I think we know it. Okay. So, now what I am saying is I have locked these modes together, and I am saying the number of modes that I am working with, capital N, is equal to 2n plus 1. So, I am working with an odd number of modes because the math becomes little easier, as you will see in the next step, if I have an odd number of modes. It does not matter. Even if it is an even number of modes, you can conveniently neglect one, right. Because remember how many modes are we going to have? 5,000, 6,000, 10,000, 20,000, something like that. Okay. So, it does not matter whether it is 20,532 or 20,531. So, we formulate using 2n plus 1 number of modes. Okay. So, here we are saying that from one mode to the next, there is a difference in frequencies, right, and we have worked out the expression earlier. What is delta nu? Delta nu, remember delta nu, what is delta nu? It is difference between the frequency of nth and the n plus 1th longitudinal mode. What is it? What is the expression? C by 2L, it is going to be handy, remember, do not forget that, that is very important. C by 2L, which is inverse of round trip time, you told me, right, C by 2L. So, what is going to be delta omega? What is delta omega going to be? You know delta nu is C by 2L, what will delta omega be? That factor of 2 pi will come, right, we are going to use this. So, do not get confused. So, this is what we are writing, E0 into e to the power I omega 0 plus k delta omega q, okay, t. What is k? K is a number that varies from minus n to plus n. So, now you already see why I want 2n plus 1 number of modes. It becomes nice symmetrically distributed about a mean, about a central position, not mean, central position. Okay. Plus we are saying k into delta phi q. What is this delta phi q? Phase difference, and that is independent of time. Let us remember that, that is very important. So, how do I expand it? I can well, e to the power a plus b is equal to e to the power a multiplied by e to the power b. So, I can use that, and I can take this E0 e to the power I omega 0 t outside the summation, and then inside I am left with e to the power I k delta omega q t plus k delta phi q. Now, I have to do this summation, and now the advantage of summing, here it is not showing, but advantage of summing k from minus n to plus n is that I know what the answer is. So, these summations, I mean, I am sure we might have done many of these in 11, 12, maybe in BSc or something, right. The summations are all nicely worked out, and it is known that sum over k equal to minus n to n e to the power I k alpha is equal to 2 multiplied by sum over k equal to 0 to n cos k alpha minus 1. And then this, you might think one summation is leading to another summation. So, what is the big deal? The big deal is that this summation is also known, as you are going to see. But let us first write it. This is what it will be. Okay? You have this outside the bracket. Inside, the summation of exponential terms becomes summation of cosines, and also sum over this domain changes, right. It was minus n to plus n, now it is going to be k equal to 0 to n. So, if you took only capital N, then we would have this trouble, you cannot even write n by 2. So, that is why we want 2n plus 1 modes. Okay. So, now all we need to know to go further is what is the summation of cosine terms? This is the summation of cosine terms. Does it look very nice? But that is what it is, what can we do, all right. So, I am going to rush through the next steps. You can do the math if you want, it is not all that difficult. So, this is what we substitute for the summation, and then we put alpha equal to delta omega q t plus delta phi q. So, in terms of alpha, this is the expression that we get. Okay. You get something like E0 e to the power I omega t, and you understand that the moment finally we do not want to work with field, right, we want to work with intensity. The moment we want to work with intensity, this e to the power I omega t is just not going to be there, because we will multiply it by its complex conjugate, that term is not going to appear. So, eventually we do not have to worry about it. We do have to worry about this sin 2n plus 1 alpha by 2 divided by sin alpha by 2, this term. Okay. So, let us write it in a little easier form. What is 2n plus 1? 2 into small n plus 1, what is that? 2n plus 1, what is that number? The answer is there in the slide. Yeah, total number of longitudinal modes, right. So, the other way we write it is capital N. So, now we have the job of this small 2n is small n is done. Let us write it in terms of capital N, and this is what we get, and here on the quality of slide also starts getting a little better. Okay. So, we get E equal to E0 e to the power I omega 0 t multiplied by sin capital N multiplied by sum of the sum of delta omega and delta phi divided by 2. Yes.
You have considered that at all frequencies the contribution to the electric field is same, the amplitude is E0.
Yes.
But is it really?
So, as I said, eventually it will not matter, because you are going to do Fourier transformation, right. You can add on the amplitudes at that time.
But the Fourier coefficients, if we are talking about them, that coefficient value should be different. If we want.
That is true, but then there is a way out there. Okay. So, this is what we end up with. The form of function is something like, if you are talking about intensity, sin nx by sin x whole square. Okay. What is x? X is this delta omega t plus delta phi divided by 2. And plot of sin nx by x sin x, I encourage you to do it using whatever graph plotting software you want to use. You will see this is what you get, and this is a kind of function that we encounter everywhere. whenever we use optics. One thing we should not forget is that this is a periodic function. I have drawn only one, but it is not going to be 1, it is going to repeat. So, you are going to get this, and this is what I was saying. The picture we drew earlier was not completely correct, in the sense that you do not just get a pulse, you get like this small, you can call after pulse if you want. Okay? But the issue is, even this picture is drawn using a comparatively smaller number of smaller values of capital N. When we really work with ultra short pulses, this duration is so small that in the same scale it is very difficult to see capital T and Tp. You get to say Tp only when you zoom in into one pulse. Okay? So, this is what it is. So, do not forget what is the x axis, what is the y axis here. So, this is what you get. Now, I have given you the answer already. Now, let us see if we can derive it. So, first let us worry about repetition rate. What is the meaning of repetition rate? We can say it is time between two maxima. Where will the first maximum occur? Sin square n x divided by sin square x. Where will that have maximum value? Of course, for that we need to work out limits, and so it is difficult, right, because it is it might sound like there is a discontinuity when x equal to 0, but it is a removable discontinuity, right. This point here, if you think, that point is going to be actually 0, is not it? 0 by 0 kind of situation, not 0, sorry, 0 by 0 is what you will get, but that discontinuity is something that you can remove. So, first maximum will occur where delta omega q T1 plus delta phi q equal to 0. Where will the next one occur? Second maximum. Okay, I will give you the answer when it is 2 pi. Does it make sense? Right? Okay. Just plug this into this expression and you will get the answer at 0 and at 2 pi. So, now if I ask you what is capital T? Capital T you can get by capital T is basically T2 minus T1. Okay. And since it is a periodic function, this separation will be same for any pair of consecutive pulses you take, right. So, what is T2 minus T1? Just subtract, delta omega q is constant. So, what do you get if you subtract one from the other? You get delta omega q multiplied by T2 minus T1, and now see delta phi q would cancel each other the moment you take a difference. That is exactly what will not happen if delta phi is also a function of time, right. You can do this only because delta phi is not a function of time and it is constant everywhere. So, what do you get? Delta omega q multiplied by T2 minus T1 is equal to 2 pi. And what is that T2 minus T1? That is capital T, time between two pulses. This one occurs at time T2, this one occurs at time T1. Okay. X axis is time multiplied by something, right. From there you can always convert to time. So, T2 minus T1 is equal to capital T. So, I can do it like this, difference in time capital T is equal to T2 minus 1. So, you get delta omega q multiplied by capital T is equal to 2 pi. So, what is T? 2 pi divided by delta omega q, right. Now, again we come back to what we promised is going to be useful later on, that later on time has come. What is delta omega q? Delta is difference, omega is angular frequency. So, it is difference in angular frequency between what and what? Two consecutive longitudinal modes, very good. And we already know some quantity associated with it, we know delta nu, and what is the relationship between delta nu and delta omega, we know that already, right. So, what we can say is we can write something like this, 2 pi divided by 2 pi into delta nu q, because delta omega is equal to 2 pi into delta nu. When you go from frequency to angular frequency, that factor of 2 pi comes. So, you are left with 1 by delta nu q. What is delta nu q? Yes. So, now from there you get 2L by C. right. So, we see that this repetition rate that we get has nothing to do with how many modes are locked. That is the nice thing that comes out, because otherwise it would have been a problem. How do you decide how many modes are available for you? Can you decide? One thing that is there is what is the spectral bandwidth? Say to start with, let us say your spontaneous emission spectrum. Okay, that is independent of anything else, spontaneous emission. Then remember, we had drawn a laser threshold where half width was delta lambda, right. So, where that laser threshold will be, who determines that? If I can somehow decrease the laser threshold, then I will have more modes that will get locked. Are you following what I am saying? This figure, this here is your laser action threshold. Okay. Now, what I am saying is that my first thing that is important is which substance, what is your active medium. That would better have a broad enough spontaneous emission band. Okay. Then what I am trying to say is, here I have placed the laser action threshold here. Is it in any way possible to push it further down? Remember, laser action means you should have stimulated emission. Is there any way for a given substance that I can increase the stimulated emission bandwidth? How can I do it? Exactly. Pump harder. If you pump harder, then this threshold can actually go down, okay, because more molecules will be excited and so on and so forth. Do not forget, the stimulated emission is like a bimolecular reaction, right, bimolecular elementary reaction between light and matter. So, you could think of doing that. Okay. So, that way you can get more longitudinal modes and you can try to get shorter pulse. That is why in a tie-sapphire laser, you want to pump with a high energy. You want to pump, if possible, by 5 watt instead of 3 watt. You want to pump, if possible, by 8 watt instead of 5 watt to get shorter and shorter pulse. Of course, there are other issues, damage is an issue, so you have to take care of those. But the problem is, if the repetition rate also depended on number of modes, there would have been an issue, isn't it? Then you do not want the repetition rate to change, otherwise synchronizing electronics, everything will change. So, it is good that repetition rate is just 2 L/C, nothing else matters. How hard you pump, nothing. Not so for pulse duration. Okay. So, for pulse duration, it is not very difficult to understand that what happens. Let us start thinking a little qualitatively. Let us go back to this analogy of people running around a field. So, when they come together, that is the pulse maximum, right. If you want a pulse of short duration, then they have to scatter faster. Okay. Now, if you have more and more people running with different speeds, will you agree with me that scattering is more efficient there? Yeah. In fact, if you look at these interferograms where you mix many waves, you will see that more the number of waves, sharper is the fall off, right. That is why you need more pulses to get a shorter pulse duration. That is a qualitative understanding. Now, let us see what we get from here. Okay. How do I define pulse duration? So, as we are, see, practically we always talk about full width at half maximum, and when we finish this discussion today, we will be talking about full width at half maximum. But for now, it is easier for us if we consider all the normal modes that are there. Otherwise, again pulse shape and all that will come. If you want to consider all the longitudinal modes that are there, you want to go from here to here, right. So, let us see what is the time about this big maximum where your intensity becomes 0 before and after. Okay. Difference between these two times is going to give me pulse duration. Remember, this pulse duration is not full width at half maximum. So, if this is 200 picosecond, that means 200 femtosecond, then full width at half maximum is perhaps 100, perhaps less, depending on the shape of the pulse. Okay. And this is where shape of the pulse also becomes important, right. If you want to go full width, do you agree with me that ratio of full width at half maximum and full width at say 10th maximum is not going to be the same for a Gaussian pulse and a Lorentzian pulse, right. They will be different. So, right now we do not worry about all that, we just talk about the pulse duration. So, when will they become 0? When the numerator is equal to 0 and the denominator is not. So, that condition is sin n delta phi t plus delta omega t plus delta phi by 2 equal to 0. Okay. This is one condition. Well, sin x equal to 0 when? When x equal to 0. Next time, when does it become 0? Yeah, pi. Okay. So, I can put time as t1, I can say this is t1. For t1, this thing is equal to 0. For t2, the next one, it is equal to pi. So, again from here you can find out t2 minus t1 very easily, and that is going to be Tp, the pulse duration. Yeah. So, do it. This is what you get, Tp equal to t2 minus t1. Just subtract. What will you get? You will get 2 pi divided by n delta omega. Is that right? Yeah. Just simple algebra, right? Again, delta omega, what does by now we are sensitized to this issue. Whenever we see delta omega, what should we do? And here this is 2 pi divided by delta omega, it is even more tempting. Go over to delta nu and you know the expression for delta nu, it turns out to be 2L by NC. So, just this n is different. So, we are vindicated. You need more number of pulses, so that this more number of not pulses, sorry, more number of longitudinal modes, because this n comes in the denominator. Okay. Larger denominator, smaller Tp, that is what you want. All right. But then we might as well have stopped here if we wanted to have only a theoretical, but finally we want to go over to something that is more tangible. Who is going to count the number of longitudinal modes? It may not be all that easy, okay, but there may be something else that is easier. So, let us use another expression, and you might have forgotten because we have talked about it I think couple of modules earlier. Remember this? In fact, we talked about it at the beginning of the previous module. As a recap, we worked out that total number of longitudinal modes, capital N, is given by 4L delta lambda divided by lambda 0 square. Okay. So, might as well substitute this. So, when you substitute, what do you get? You get pulse duration is equal to lambda 0 square divided by 2c delta lambda. Okay. What is delta lambda? In the treatment that we have followed, delta lambda is half width at half maximum of the spontaneous emission band, but what is more important for us is that it is the half width at the base of the stimulated emission band, half width at base. Yeah. Okay. So, now we have something tangible, right? We can measure spectrum. When we measure spectrum, we know what lambda 0 is, we know what delta lambda is. So, it is not very difficult to figure out what the pulse width is going to be. That is why in our lab we do not bother about trying to measure the pulse width in time domain. As I said, shortly we are going to discuss how to do it. So, see what the problem is. We are talking about short pulses, 100 femtosecond, 50 femtosecond, 6 femtosecond. How will you measure? You cannot see it on an oscilloscope directly. Okay? So, you have to apply some kind of a trick, and the trick that is applied invariably depends on some instrument that was made long ago. Okay, let me digress a little bit. I love digression. What is the speed of light? Is that large or is that small? How do you know it is correct? Who told you that that is the speed of light? I mean, textbooks told you, but how do they know? Somebody must have measured it, right? So, if I want to measure what is the speed of Somodipto, it is very easy. I can do it using perhaps my wristwatch. What is the wristwatch or what is the stopwatch that allowed somebody to measure the speed of light? Again, everybody has studied in the 9, 10, 11, 12 sometime in physics. Michelson interferometer. The moment I say it, you will know. It is just that you might know it as Michelson interferometer. Michelson interferometer, right? So, in Michelson interferometer, if you remember, monochromatic light was used and there was a relationship from which you could find out the from path length. So, basically what Michelson interferometer does is it generates a map, like we generate a map of the fluorescence decay that takes place in femtosecond by monitoring second harmonic intensity as a function of delay time. So, Michelson interferometer also generates a map, okay, and it sort of stretches out, does not stretch out, it behaves as if it stretches out and creates a wave whose wavelength is correlated with the wavelength that falls on it. Okay, there is a relationship, it is not very difficult to work out. So, that is how speed of light was determined. So, now once you know the speed of light, you can determine small times using Michelson interferometer kind of arrangement. We will talk about that, but it is a little cumbersome, and I do not know how many chemistry ultrafast labs in India at all have what is called an autocorrelator. It is called an autocorrelator. The instrument by which you measure the pulse width is called an autocorrelator, and we are happily working in this field without ever having had one. Why? Because this is our saving grace. Tp is 4L delta lambda divided by lambda 0 square. So, if delta lambda, because if delta lambda is of some value, in principle we can calculate what the pulse width is, right. If we do not want to calculate what the pulse width is, we can get some qualitative value. We know from our experience that for a 100 femtosecond pulse laser, your full width at half maximum has to be 12 nanometer or so. For the amplifier, which is a shorter pulse laser, full width at half maximum has to be more. Okay. This is a relationship that one can use and work happily in an ultrafast lab without ever having to buy an autocorrelator. All right. But then it may not be as simple as I have proposed it to be, because do not forget what this delta lambda is. It is the basal width, right. One thing that we have not considered so far at all is the spectral shape, that is actually important. So, let us close today's discussion by talking about it. So, what we are essentially talking about is transform limited pulses, and I have goofed up a little bit on this slide, unfortunately, bear with me. See, what are we saying? We are saying that a broader spread in wavelength and therefore energy corresponds to a shorter spread in time. Okay? That is essentially something that is absolutely correlated with uncertainty principle once again. Greater uncertainty in time is associated with lesser uncertainty in energy and vice versa. Okay? So, these are called transform limited pulses. Of course, this is the best case scenario. You might have a bandwidth, full width of maximum of 12 nanometer, but not 100 femtosecond pulse if something else is wrong. Right now, we are talking about the best case scenario. So, let us see why they are called transform limited pulses. Let us start talking about a Gaussian pulse in time domain. Okay, this is a Gaussian function. If I want to know its spectrum, if I want to know what that pulse looks like in frequency domain, what do? We do Fourier transformation. And when you do Fourier transformation, what kind of function do you get? Another Gaussian. Okay? And this thing that I had by mistake written earlier is that full width half maximum, delta omega full width half maximum, that is given by this kind of a function. Okay? What is the spread in time for this Gaussian function in time? The spread is given by 2 tau square root of ln2. All right. Now, if I multiply the two together, full width half maximum in time domain multiplied by full width half maximum in frequency domain, what do I get? I get 0.441. All this tau and everything cancel off, ln2 is a number. Okay. So, a transform limited pulse which is Gaussian is going to obey this. So, if your pulse is Gaussian, then it is very nice. Again, no need of an autocorrelator. The only thing to remember is you should talk about delta nu, not delta lambda. Okay? Lambda is an inverse scale, right? That is why that lambda 0 square factor comes. So, delta t full width half maximum in time multiplied by full width half maximum in frequency gives 0.441 for Gaussian for a transform limited pulse. So, what is it? Why do people buy autocorrelators in the first place? So far, I have told you that we are happily working without an autocorrelator, without having to spend those few lakhs of rupees that are required to buy it or build it. Why do people buy at all? They buy it because not all pulses are transform limited pulses. This is sort of the theoretical limit. Okay? And then let us now close by showing you something else. This number 0.441 that we got, why did we get 0.441 and not 0.8? Because we worked with Gaussian function. Okay? So, similarly, this has been worked out for other pulses as well, and these are the numbers. Forget about this for now. For a square pulse, the product has to be 1. For a diffractive pulse, 0.886. Gaussian we have discussed already. For hyperbolic second, these are all different shapes, right? And there is no guarantee that one shape that always you are going to work with Gaussian kind of pulses. Lorentzian 0.221. See, Gaussian and Lorentzian we are very familiar with. See the difference is one is half of the other. Exponential, two-sided exponential, the product is 0.142. Right? So, depending on what kind of pulse you have, what kind of spectrum you have, in principle you can work out the pulse width if you just look at the spectrum, provided you are working with transform limited pulses. Okay. So, that is what we wanted to discuss today. Next, let us see how to achieve. We have talked about Modelocking, we have talked about the theory, but how do you do it? That is what we are going to discuss in the next few modules.